Some say it's a call for freedom. Others say it's a call for genocide. From the river to the sea, Palestine will be free. That phrase has been heard in city streets across the world. Well, biblical scholar Mark Turnage spoke with Ashley Key to unpack the dangerous ideology.
They said it was absolutely impossible. A dying nation where families fought over water and children cried from thirst. Then Israel did the unthinkable. They carved a 12,000-kilometer river through pure desert, moving billions of liters of ocean water inland. But here's the shocking part. They turned that deadly salt water into crystal-clear drinking water using secret technology that scientists said could never work. What happened next changed everything.
Had, 20, 30,000 people praying, but from 183 countries. So pray wherever you are. Get your church praying, your Bible study praying, and be those watchmen on the walls of Jerusalem. Secondly is your financial gifts to help Israel. There are needs in Israel. The government can only do so much, and especially...
The Negev Desert stretches across southern Israel like a vast golden ocean, covering more than half the country's total land area. For most of human history, this place was considered uninhabitable. Summer temperatures regularly climb past 43 degrees Celsius, rainfall is scarce and unpredictable, and the landscape offers little more than rocks, sand, and relentless sunshine. Yet, despite these harsh conditions, Israel embarked on one of the most ambitious water engineering projects the world has ever seen. The story begins in the early decades of Israel's existence as a nation. Water scarcity wasn't just an inconvenience, it was an existential threat. The country's population was growing rapidly, agriculture was expanding, and traditional water sources were running dry. Underground aquifers that had sustained communities for generations were being depleted faster than nature could replenish them. Rivers in the region were few and often shared with neighbouring countries, leading to diplomatic tensions and uncertain supply. Meanwhile, just a few dozen kilometres to the west lay the Mediterranean Sea, containing essentially unlimited water, though obviously not in a form anyone could drink or use for crops. The contrast was striking and frustrating. On one side, a nation struggling with chronic water shortages. On the other, an enormous body of water that seemed tantalizingly close, yet completely unusable. This geographical irony sparked an idea that many considered impossible at the time. What if Israel could somehow bring that seawater inland, deep into the heart of the desert, and then transform it into fresh, drinkable water? The concept seemed almost absurd given the scale and technological challenges involved, but Israeli engineers and planners believed it could be done. The official approval for what would become known as the National Water Carrier Project came around the turn of the millennium, though planning had been underway for years before that. The government committed nearly $3 billion to the venture, an enormous sum that reflected both the desperate need and the project's staggering ambition. The plan called for constructing over 12,000 kilometers of canals, pipelines, and infrastructure to move water from the coast to the interior. This wasn't just about building a single canal. It required creating an entire artificial river system, complete with pumping stations, treatment facilities, and distribution networks. To understand why Israel was willing to invest so heavily in this project, you need to appreciate just how dire the water situation had become. In the Negev Desert, which makes up roughly 60% of Israel's territory, farming was nearly impossible without irrigation. Families in remote settlements relied on water delivered by truck, sometimes waiting days between shipments. Agriculture, which many considered essential for the young nation's food security and economy, was constantly on the edge of collapse. Cities were implementing strict rationing. The country's leaders knew that without a dramatic solution, Israel's growth and perhaps even its survival would be severely limited. The Mediterranean Sea offered a potential answer, but only if two massive challenges could be overcome. First, the water had to be physically transported across hundreds of kilometers of difficult terrain. Second, and perhaps more daunting, the salt had to be removed. Seawater contains about 35,000 parts per million of dissolved salts. Humans can only safely drink water with less than 500 parts per million. That meant removing more than 98% of the salt, and doing so on an industrial scale that could supply millions of people. The technology for desalination, the process of removing salt from seawater, had existed in various forms for decades, but never at the scale Israel needed. Early desalination plants were expensive to operate, energy-intensive, and produced relatively small amounts of water. However, advances in reverse osmosis technology during the late 20th century made large-scale desalination increasingly feasible. Reverse osmosis works by forcing seawater through special membranes at high pressure. These membranes have microscopic pores that allow water molecules to pass through while blocking salt ions and other contaminants. While the basic principle is straightforward, implementing it effectively requires sophisticated engineering and constant monitoring. Israel had already been experimenting with desalination on a smaller scale, but the National Water Carrier project would require facilities far larger than anything previously built. The plan called for massive desalination plants along the Mediterranean coast, each capable of processing hundreds of millions of liters of seawater per day. These plants would work around the clock, drawing in seawater, removing the salt and impurities, and pumping out fresh water that could be distributed throughout the country. But desalination was only half the equation. The fresh water still needed to get from the coastal plants to the places where it was needed most, particularly the agricultural regions in the south. This meant constructing an artificial river that would flow through one of the world's harshest deserts. The engineering challenges were immense. The canal would need to traverse sand dunes, rocky outcrops, and varying elevations. It would be exposed to extreme heat, sandstorms, and the constant threat of evaporation. Every aspect of the design had to account for the brutal environment. The historical context makes this project even more remarkable. Israel is a relatively small country with limited natural resources. It lacks the vast oil wealth of some of its neighbors, and it faced ongoing security concerns that consumed significant portions of the national budget. Yet the government chose to prioritize this water infrastructure project, viewing it as essential for the nation's future. The decision reflected a broader philosophy that Israel couldn't rely on nature to provide water. It would have to create its own solutions through technology and innovation. Similar water challenges have faced many countries throughout history, but few have attempted solutions on this scale. Ancient civilizations built impressive aqueducts and irrigation systems, but nothing comparable to moving seawater hundreds of kilometers inland and transforming it at an industrial scale. Some pointed to projects like the Great Man-Made River in Libya, which also moved water across desert terrain. But that project relied on tapping underground fossil water, not desalinating seawater. Israel's approach was fundamentally different, and arguably more sustainable. Since seawater is essentially inexhaustible, the vision was audacious: transform the Negev Desert from a barren wasteland into productive agricultural land, ensure reliable water supplies for growing cities, reduce dependence on increasingly stressed natural water sources, create food security for a nation that imports much of what it eats, and do all of this in a way that could potentially be replicated by other water-scarce countries facing similar challenges. Critics raised valid concerns. The energy requirements for pumping and desalinating such massive quantities of water would be enormous. The environmental impact on Mediterranean marine life near the intake facilities needed careful management. The concentrated brine left over from desalination would need to be disposed of properly to avoid harming coastal ecosystems. The financial burden might prove unsustainable, and there was always the risk that the technology simply wouldn't work at the required scale, turning the entire project into an expensive failure. Yet the planners pressed forward, confident that the alternatives were worse. Doing nothing meant accepting permanent water scarcity and all the limitations that came with it. Relying solely on conservation and efficiency improvements wouldn't be enough given population growth projections. Depending on water from neighbouring countries introduced political vulnerabilities. The only path forward, they believed, was to take control of their own water destiny through this massive engineering undertaking. As construction finally began, few could fully imagine what the completed project would look like, or how it would transform the country. Workers were about to begin one of the largest earth-moving operations in modern history, carving artificial rivers through solid desert, all to make water flow where nature never intended it to go. Before any water could flow and before any desalination plant could operate, engineers faced a fundamental challenge that had nothing to do with advanced technology. They needed to prepare the ground itself. The Negev Desert wasn't just hot and dry, it was actively hostile to large-scale construction. The sand shifted constantly with the wind, temperatures swung wildly between day and night, and the terrain offered almost no natural stability. Building a canal system hundreds of kilometers long through this environment required solving problems that most construction projects never encounter. The planning phase alone took years and involved technology that would have seemed like science fiction just decades earlier. Engineers used high-resolution satellite imagery to map the entire route, identifying potential obstacles and planning the path of least resistance. Ground-penetrating radar helped them understand what lay beneath the surface, revealing hidden rock formations, underground voids, and variations in soil density that could affect construction. Weather stations were established at intervals along the proposed route to measure wind patterns, because sandstorms capable of burying equipment overnight were a constant threat. Survey teams spent months living in the desert, enduring conditions that tested human endurance. They drilled hundreds of boreholes, some extending more than 30 meters into the earth, extracting core samples that revealed the geological layers hidden beneath the sand. Every sample was analyzed in laboratories to determine its composition, strength, and water content. This information was critical for understanding where the ground could support heavy machinery and where additional reinforcement would be needed. The teams worked with GPS equipment that could measure positions down to the centimeter, placing thousands of markers that would guide construction crews in the months to come. Mapping wind patterns proved particularly crucial. Unlike construction sites in more temperate climates, the Negev presented the unique problem of terrain that could literally disappear overnight. Wind corridors, areas where prevailing winds consistently moved large quantities of sand, had to be identified and avoided. Construction in these zones would be futile, as a single major sandstorm could bury weeks of work under meters of sand. The survey data allowed engineers to route the canal around the most problematic areas, even if it meant adding distance to the overall length. Once the route was finalized and marked, the real work began. Hundreds of bulldozers were brought to the desert, forming what must have looked like a mechanical army advancing across the dunes. These weren't ordinary construction dozers, but specialized machines designed to handle extreme conditions. Their task was to level the dunes, cutting down the high ridges and using that sand to fill in the lower areas. The goal was to create a relatively flat, stable surface that could support the heavier equipment that would follow. The scale of Earth movement was staggering. Engineers estimated that approximately 70,000 tons of sand and soil needed to be moved every single day to stay on schedule. That's roughly equivalent to filling 7,000 dump trucks daily. The work proceeded in sections, with crews leapfrogging along the route. Surveyors constantly checked elevations to ensure the surface remained level within very tight tolerances. Even small variations could cause problems later when water began flowing, as uneven grades could create areas of turbulence or stagnation. But leveling the dunes was only the beginning. Loose sand, even when flattened, cannot support the weight of concrete mixers, crane trucks, and other heavy construction equipment. The sand needed to be stabilized, transformed from a shifting surface into something solid enough to work on. Engineers developed a technique that might seem counterintuitive in a desert. They added water. Water injection systems were installed along the prepared sections. Long sprinkler arms and underground pipes distributed controlled amounts of water across the surface, allowing moisture to penetrate several inches deep. The water acted as a binding agent, causing the sand grains to stick together and form a more cohesive layer. This wasn't about creating mud. The amount of water was carefully calculated to achieve just the right level of dampness. Too little, and the sand would remain loose. Too much, and the surface would become unstable in a different way. Once the sand reached optimal moisture content, heavy compaction equipment moved in. Steel drum rollers, some weighing 20 tons or more, made repeated passes over every section. The constant pressure squeezed out air pockets and forced the moistened sand grains tightly together. The rumbling of these machines echoed across the desert as they worked methodically back and forth. Each pass made the surface incrementally harder until, after dozens of passes, the once loose sand had been transformed into a firm base capable of supporting heavy loads. The compacted surface would then be left to dry under the intense desert sun. As the moisture evaporated, the sand hardened further, creating a stable platform that could handle the punishment of round-the-clock construction activity. This process had to be repeated along the entire length of the canal route, section by section, month after month. With the foundation prepared, the actual excavation could begin. This phase represented one of the largest digging operations ever undertaken in Israel. The canal needed to be wide and deep enough to carry enormous volumes of water, yet precisely shaped to ensure efficient flow. Engineers designed a U-shaped profile, approximately 45 meters wide at the base, and averaging 7 meters in depth. These dimensions weren't arbitrary, but carefully calculated based on the required water volume and flow rate. More than 1,200 workers were deployed to the excavation sites, working in rotating shifts that kept the project moving 24 hours a day. The desert heat was punishing, with daytime temperatures often exceeding 46 degrees Celsius. Night shifts offered cooler conditions but presented their own challenges, as working in darkness with heavy machinery required extra caution and sophisticated lighting systems. The excavation had to follow an incredibly precise grade. For the water to flow naturally without requiring constant pumping, the canal floor needed to slope at just the right angle. The specification called for a drop of approximately 1 inch per 100 feet, maintained consistently over distances of hundreds of kilometers. This required constant monitoring by survey crews using laser leveling instruments. Every 48 meters, measurements were taken and compared against the design specifications. Any deviation, even by a few centimeters, needed to be corrected immediately. The excavated material couldn't simply be discarded. In many sections, it was used to build up embankments along both sides of the canal. These raised walls, ranging from 3 to 5 meters high, would help contain the water and protect surrounding areas from overflow. The embankments also served as service roads, allowing maintenance vehicles to access the canal along its entire length. Not all sections of the route offered the same conditions. In some areas, the excavation crews encountered solid rock that required blasting before it could be removed. In others, they found soil so soft and unstable that it threatened to collapse back into the canal as fast as it could be dug out. These weak zones required special treatment. Engineers would drill deep holes and drive in sand piles, essentially creating artificial pillars that extended down to more stable layers. In the most problematic areas, they mixed cement with clay and pumped it into the ground to create a strengthened foundation that could support the canal structure. The construction corridor stretched for hundreds of kilometers across the desert, and managing this vast workspace required its own infrastructure. Concrete batching plants were established at intervals to supply the enormous quantities of concrete that would be needed for lining the canal. Mechanical workshops were set up to maintain and repair the fleet of heavy equipment. Worker camps provided accommodation for crews who lived on site for weeks at a time. Supply convoys ran constantly, bringing in fuel, spare parts, food, and water for the workers themselves. From above, the construction site would have appeared as a long scar across the desert landscape, a thin brown line stretching toward the horizon. Along that line, dozens of combos, excavators worked simultaneously, their buckets rising and falling in mechanical rhythm. Dump trucks formed continuous chains, hauling material away from the digging sites to the dumping areas. Dust clouds rose continuously, visible for kilometers in every direction. It was an industrial ballet, performed on a massive scale, with hundreds of machines and thousands of workers coordinating their efforts toward a single goal. This excavation phase lasted for many months, proceeding through summer heat and winter cold. Sandstorms occasionally forced temporary shutdowns, covering equipment and filling in sections that had to be re-excavated. Equipment breakdowns were common given the harsh conditions, and keeping the machinery running required constant maintenance. Workers fell ill from heat exhaustion despite precautions, and accidents were an ever-present danger when operating heavy machinery in such difficult conditions. Yet slowly, steadily, the shape of an artificial river emerged from the desert floor. What had been flat sand was now a long, precisely engineered trench, waiting for the next phase of construction that would transform it from a simple ditch into a sealed waterway capable of carrying life across one of the world's most unforgiving landscapes. The excavated trench, stretching across the Negev, represented an impressive feat of engineering, but it was far from complete. A simple ditch carved through desert sand, no matter how precisely shaped, could never function as a reliable water channel. The desert sand acts like a sponge, capable of absorbing enormous quantities of water within hours. Without proper sealing, any water poured into the canal would simply disappear into the ground, wasted before it could reach its destination. The lining phase would prove to be one of the most critical stages of the entire project. Engineers began by preparing the canal bed and slopes with meticulous care. A layer of fine sand, approximately 5 centimeters thick, was spread evenly across the bottom and sides of the canal. This sand was moistened and carefully leveled to create a smooth, uniform surface. Any irregularities, bumps, or depressions could create weak points in the lining that would follow. Workers used specialized equipment to ensure the surface met exact specifications, checking and rechecking their work before proceeding to the next step. The primary waterproofing system consisted of reinforced concrete panels. These weren't poured in one continuous pour, which would have been impractical and prone to cracking, but rather constructed as individual sections. Each panel measured roughly 5 meters long by 3 meters wide and was between 10 and 13 centimeters thick. The concrete mixture itself was specially formulated to withstand the extreme temperature variations of the desert environment, where surfaces can be scorching hot during the day and surprisingly cold at night. Creating these panels in the middle of the desert presented its own set of challenges. Concrete requires water to cure properly, yet water was precisely what the project was trying to conserve and transport. The timing of pours had to be carefully managed to avoid the hottest parts of the day when rapid evaporation would compromise the concrete strength. Workers often began their shifts before dawn, taking advantage of cooler morning temperatures to place and finish the concrete while conditions were optimal. Between each concrete panel, expansion joints were installed. These joints serve a crucial function that might not be immediately obvious. Concrete expands and contracts with temperature changes, and in the desert, those temperature swings can be dramatic. Without expansion joints, the concrete panels would crack as they expanded in the heat or contracted in the cold. The joints were filled with hot bitumen sealant, a tar-like material that remains flexible across a wide temperature range. This flexibility allows the panels to move slightly without breaking the waterproof seal. In areas where geological surveys had identified particularly unstable subsoil, engineers added an extra layer of protection beneath the concrete. High-density polyethylene geomembrane, essentially a thick plastic sheet, was laid down first. This material is impermeable to water and provides an additional barrier against seepage. The geomembrane was fixed in place with steel anchors driven into the ground, then covered with a protective cushion of sand before the concrete panels were poured on top. This double-layer system ensured that even if the concrete developed hairline cracks over time, the underlying membrane would continue to prevent water loss. The scale of the lining operation was enormous. More than 350 kilometers of canal required waterproofing. Teams worked in sections, completing one segment before moving on to the next. Quality control inspectors followed behind, testing the seals between panels, checking for any gaps or weaknesses, and verifying that the work met specifications. Any section that failed inspection had to be redone, regardless of the time or expense involved. There was no margin for error, as even small leaks multiplied across hundreds of kilometers would result in massive water losses. Along the embankments on both sides of the canal, engineers implemented erosion control measures. The desert wind constantly moved sand, and without intervention, the embankments would gradually erode, with sand sliding down into the canal. To prevent this, they planted vetiver grass and desert acacia along the slopes. These plants have deep root systems that bind the soil together, creating natural reinforcement against erosion. Vetiver grass in particular is remarkably hardy, able to survive with minimal water once established, and its dense root network can extend several meters into the ground. From an aerial view, the completed sections of canal appeared as a gleaming silver ribbon cutting through golden sand. The concrete surface reflected the intense desert sunlight, making the canal visible from considerable distances. It was a stark contrast. This geometric precision imposed on the organic chaos of the desert landscape. The canal represented human determination made physical, a declaration that water would flow here despite every natural obstacle. But a canal alone cannot function as a complete water distribution system. Hundreds of auxiliary structures were needed to control, regulate, and direct the water flow. At the system's origin point, where water enters from the desalination facilities, engineers constructed head regulators. These are massive concrete structures housing multiple steel gates that control how much water flows into the canal. The gates can be raised or lowered to adjust the flow rate based on demand and system capacity. Along the main canal route, more than 900 separate engineering components were built, reinforced. Concrete bridges carried roads and railways over the canal, maintaining transportation links that the canal would otherwise sever. Some of these bridges were simple beam structures, while others in high-traffic areas were more elaborate, designed to handle heavy vehicles and constant use. Each bridge required its own foundation work, with pilings driven deep into the ground to provide stable support. Spillways were constructed at regular intervals as safety measures. These are overflow channels that allow excess water to be diverted away from the main canal if water levels rise too high. Without spillways, flooding could damage the canal structure or surrounding areas. The spillways are designed to activate automatically when water reaches a certain level, requiring no human intervention to function. Perhaps the most technically complex structures were the siphons and aqueducts, built wherever the canal needed to cross natural waterways. The desert may be dry most of the year, but when rain does fall, it can create sudden flash floods. Natural wadis, dry riverbeds that only flow during storms, crisscross the landscape. The canal had to accommodate these natural drainage patterns without disruption. Siphons are inverted sections of canal that dip underground, allowing the natural watercourse to flow overhead. Aqueducts work in reverse, carrying the canal water above ground level, while the natural drainage passes underneath through large culverts. Distribution gates were installed every 10 to 15 kilometres along the main canal. These smaller gate structures allow water to be diverted into secondary channels that branch off to serve specific regions or communities. Each gate is equipped with flow meters and can be controlled remotely, allowing operators to adjust water distribution across the entire system from a central control facility. This level of control is essential for managing a network of this complexity, ensuring that water reaches where it's needed, while preventing waste. The construction of these auxiliary structures required different specialized teams. Bridge builders, gate manufacturers, and concrete specialists all worked simultaneously at different points along the canal. Coordinating their efforts required sophisticated project management and communication systems. Delays in one section could cascade through the entire project timeline, so maintaining schedule adherence was a constant preoccupation for project managers. After years of construction, with thousands of workers having contributed their labor and expertise, the system was finally ready for its first test. The moment when water would actually flow through the canal for the first time carried enormous significance. This wasn't just an engineering test, but a symbolic moment for everyone who had invested hope in the project's success. Engineers approached the initial water introduction with extreme caution. They opened the head gates gradually, allowing water to enter the canal in controlled amounts. The first sections received only a small flow, perhaps 500 cubic meters per second. Technical teams positioned themselves at intervals along the canal, equipped with instruments to measure water pressure, flow velocity, and any signs of structural problems. They watched the embankments carefully for any indication of movement or instability. They checked the concrete lining for leaks, marking any spots where water seeped through for later repair. As the initial test sections proved stable, the flow rate was gradually increased, first to 2,000 cubic meters per second, then to 6,000. With each increase, the monitoring teams recorded hundreds of data points, building a comprehensive picture of how the system performed under different conditions. Every measurement was compared against design specifications and computer models that had predicted how the canal should behave. The water moved slowly at first, spreading along the canal bed in a thin sheet that gradually deepened. The sight of actual water flowing through the desert, water that would soon sustain farms and cities, was profound for those who witnessed it. Workers who had spent months or years laboring under the brutal sun watched as their efforts were validated. Engineers who had calculated and recalculated every dimension saw their designs come to life. When water finally reached the furthest sections of the canal, areas deep in the Negev that had been perpetually dry, local communities erupted in celebration. People gathered along the canal banks, some crying, others cheering, all of them understanding that they were witnessing a transformation. This wasn't just water flowing, it was possibility flowing, opportunity flowing, life itself flowing into places where it had never existed before. Farmers who had abandoned their land due to drought returned to stake new claims. Families who had relied on truck-delivered water could scarcely believe they would have reliable access. The canal represented hope made tangible, engineering made meaningful. Yet the water flowing through the canal was still seawater, still laden with salt that made it useless for drinking or agriculture. The canal was merely the delivery system. The real transformation would occur in the technological heart of the operation, the desalination plants, where Mediterranean seawater would be stripped of its salt and reborn as fresh water capable of sustaining a nation. The water flowing through the artificial river that now cuts across the Negev Desert carries, within it, a fundamental problem. Despite all the engineering marvels that brought it this far, despite the excavation, the concrete lining, and the sophisticated control systems, the water remains unusable. Seawater contains approximately 35 grams of dissolved salts per liter, a concentration that makes it deadly for crops and toxic for human consumption. Before this water can fulfill its purpose, it must undergo a complete transformation, and that transformation happens in facilities that represent some of the most advanced water treatment technology ever deployed. The desalination plants along Israel's Mediterranean coast are industrial complexes on a scale that's difficult to comprehend without seeing them in person. These facilities operate continuously, processing hundreds of millions of liters of seawater every single day. The largest among them can produce enough fresh water to supply several million people, running 24 hours a day, 7 days a week, stopping only for scheduled maintenance. They represent a different kind of engineering challenge than the canal itself, one focused not on moving earth but on manipulating water at the molecular level. The process begins at intake facilities extending into the Mediterranean. Seawater is drawn through large pipes positioned well offshore and at significant depth. This location isn't random but carefully chosen to avoid the most biologically active zones near the surface and shoreline. The intake structures are designed to minimize impact on marine life, using relatively slow flow velocities and screens that prevent larger organisms from being drawn in. Environmental monitoring around these intakes is constant, ensuring that the operation doesn't significantly harm the local ecosystem. Once inside the facility, the seawater enters the pre-treatment phase. Despite coming from the open ocean, seawater is far from clean in the technical sense. It contains suspended sediments, organic matter, algae, bacteria, plankton, and sometimes oil residues from shipping activity. All of this must be removed before the water reaches the sensitive equipment in later stages. The pre-treatment area looks like a maze of large tanks and basins where the water flows slowly, allowing heavier particles to settle out by gravity. Chemical coagulants are added to help smaller particles clump together and sink. Oil water separators use the different densities of oil and water to skim off any petroleum contaminants. This is particularly important along shipping routes, where small amounts of fuel oil can contaminate seawater. The separated oil is collected and disposed of properly, while the cleaned water moves forward. Even after these initial steps, the water still contains countless microscopic particles and organisms that could cause problems downstream. The fine filtration stage employs banks of membrane filters that look like enormous arrays of black tubes. These are hollow fiber membranes, with walls so thin and pores so small they can trap particles measured in microns. A micron is 1/1,000,000th of a meter, and these filters can catch particles just a few microns across. Algae cells, bacteria, viruses, and any remaining suspended sediments are blocked while water passes through. The membranes require regular cleaning to prevent clogging, and they're periodically backwashed, forcing clean water backward through the fibers to flush out accumulated debris. After pre-treatment and fine filtration, the water is cleaner than most natural freshwater sources, but it's still seawater, still saturated with dissolved salts that fine filters cannot remove. This is where the heart of the desalination process comes into play, the reverse osmosis system. The name itself reveals something about how the process works. Osmosis is a natural phenomenon where water moves through a membrane from areas of low salt concentration to high salt concentration, trying to equalize the concentrations on both sides. Reverse osmosis does exactly what the name suggests. It reverses this natural process by applying pressure to force water from the high salt side to the low salt side. The reverse osmosis membranes are marvels of materials science. They appear as long cylindrical modules, each housing spiral-wound sheets of semi-permeable membrane material. The pores in these membranes are measured in nanometers, billionths of a meter, approximately 100 times smaller than a virus. These pores are large enough to allow water molecules to squeeze through, but too small for the hydrated salt ions dissolved in seawater. When you consider that a sodium or chloride ion surrounded by its shell of water molecules is about half a nanometer across, you begin to appreciate the precision involved. But getting water to move through these impossibly tiny pores requires enormous pressure. High-pressure pumps generate pressures of 60 to 80 bars, roughly equivalent to the water pressure you would experience if you dove to a depth of 600 to 800 meters below the ocean surface. Under this intense pressure, water molecules are literally forced through the membrane pores while everything larger is left behind. The water that emerges on the other side is astonishingly pure, containing less than 500 parts per million of total dissolved solids, compared to the 35,000 parts per million it started with. The salt and other substances that don't pass through the membrane create an increasingly concentrated brine solution. This brine must be carefully managed because simply dumping highly concentrated salt water back into the ocean could harm marine life near the discharge point. Israeli facilities dilute the brine with cooling water from power plants or spread the discharge over large areas using diffuser systems that ensure rapid mixing with ambient seawater. Environmental monitoring programs track the impact continuously, and discharge rates are adjusted to maintain ecological balance. The pure water emerging from the reverse osmosis modules might seem perfect, but it actually presents a new problem. It's too pure. Water with almost no dissolved minerals is chemically aggressive, meaning it will leach minerals from pipes and potentially create health issues if consumed over long periods. Human bodies need certain minerals, particularly calcium and magnesium, that we normally get partly from drinking water. Water that's been stripped of everything needs to be remineralized to become properly balanced for human use. Precise dosing systems add back controlled amounts of minerals. Calcium and magnesium compounds are dissolved into the water, raising the hardness to appropriate levels. The pH is adjusted to a neutral range, typically around 7 to 8, making the water neither acidic nor alkaline. These adjustments transform the water from a chemical curiosity into something that tastes clean and fresh. Water that feels normal to drink despite having started its journey as seawater. Disinfection is the final critical step before water enters the distribution system. Even though the reverse osmosis process removes virtually all microorganisms, absolute certainty is required when dealing with drinking water for millions of people. Ultraviolet light systems expose the water to intense UV radiation that damages the DNA of any remaining bacteria or viruses, rendering them unable to reproduce or cause infection. Some facilities also use ozone treatment, a powerful oxidizing agent that destroys microorganisms and breaks down any trace organic compounds that might have survived earlier treatment stages. A small amount of chlorine is added as the water enters storage tanks and distribution pipes. This residual chlorine, typically just a few parts per million, provides ongoing protection throughout the journey, from the treatment plant to people's taps. It's the same approach used in conventional water treatment systems worldwide, and ensures that water remains safe, even if it sits in pipes for hours or days. Throughout the entire process, from intake to final distribution, monitoring systems track hundreds of parameters in real time. Sensors measure salinity, pressure, flow rate, temperature, pH, turbidity, and chlorine levels at multiple points. Automated systems can detect problems within seconds and make adjustments or shut down sections of the plant if needed. Laboratory technicians also perform regular manual testing, analyzing samples to verify that automated readings are accurate and that water quality meets or exceeds all regulatory standards. The scale of these operations is staggering when you consider the numbers. A large desalination plant might process 600,000 cubic meters of water per day, That's enough to fill 240 Olympic-sized swimming pools every 24 hours. The energy requirements are equally impressive, with modern facilities consuming roughly 3 to 4 kilowatt-hours of electricity for every cubic meter of fresh water produced. This energy demand has driven Israeli engineers to develop increasingly efficient systems, incorporating energy recovery devices that capture pressure from the concentrated brine stream and use it to help pressurize incoming seawater. Once the water leaves the desalination plants, it enters the National Water Carrier System, a network of pipes, canals, pumping stations, and storage facilities that distributes water throughout Israel. The water that was seawater just hours earlier now flows south through the very canals built across the Negev, joining water from other sources in an integrated system that supplies the entire country. Sophisticated control rooms monitor flow and pressure across the network, directing water where it's needed most. The impact on Israeli agriculture has been transformative. Regions of the Negev that were considered hopelessly arid now support extensive farming operations. The Israelis didn't just bring water to the desert, they revolutionized how that water is used. Drip irrigation systems, largely developed and perfected in Israel, deliver water directly to plant roots with minimal waste. Sensors monitor soil moisture, and computerized systems adjust water delivery based on actual plant needs rather than schedules. This precision agriculture means that every drop of expensively produced desalinated water is used as efficiently as possible. Crops that once seemed impossible to grow in the Negev now thrive. Tomatoes, peppers, dates, citrus fruits, and even water-intensive crops like melons are cultivated successfully. Greenhouses dot the landscape, their climate-controlled environments using comparatively little water while producing yields far higher than traditional farming. The sight of green fields and orchards in the middle of the desert, all sustained by water that began as Mediterranean seawater, represents a complete reversal of the natural order, achieved through human ingenuity and determination. Beyond agriculture, the reliable water supply has enabled population centers to grow and prosper in areas that were previously marginal at best. Towns that once depended on trucked water or severely limited supplies now have abundant clean water for homes, schools, hospitals, and industry. The psychological impact of this security shouldn't be underestimated. When people know water will flow from their taps reliably, it changes how they think about their future and their ability to build lives in challenging environments. The Israeli approach to solving water scarcity through massive desalination and distribution infrastructure has attracted attention from around the world. Many countries face similar challenges as populations grow, climate patterns shift, and traditional water sources become stressed. Delegations from China, India, Australia, California, and numerous other water-scarce regions have studied the Israeli system, looking for lessons they might apply in their own contexts. What Israel accomplished was more than an engineering project. It was a fundamental reimagining of the relationship between human civilization and natural constraints. For millennia, human settlements were bound to water sources. You lived where water was, and if water disappeared, you left. Israel demonstrated that with sufficient technology, investment, and determination, this ancient limitation could be overcome. The desert doesn't have to be permanent. Water can be created where none existed before, and life can flourish in the harshest environments when human creativity is applied to natural challenges.